Okay, everybody, here's your video that's on exponents and scientific notation. I know that we haven't really talked about this a lot in class. I gave you a couple of videos to watch on exponents. I haven't talked a lot about scientific notation, but let's go ahead and do that. Scientific notation is a way to write a really large or really small number. This is done by writing a number using digits, the decimal point, and exponents. You use this when you are writing about really big and really small numbers because otherwise writing numbers in standard form or the usual way would just get extraordinarily cumbersome. For example, the US government spent $3.7 trillion this year as a regular number in standard form. This is written with a 3700 and then another 9 zeros beyond that. So to write this number in scientific notation, what we would do is let me magnify this really quick so that you can see it a little bit better. What I would do is I would put instead of this comma right here, I would replace that with a decimal point. And then after that decimal point, I would count how many digits there are past the decimal point, including the non-zero number. So in this instance, that's 12 numbers, which leads me to writing that as 3.7 times 10 to the 12th power. This also works for very small numbers. Let's say the number is, I just gave a very simple one. This is really just 12 hundredths. 12 hundredths would be written as 1.2 times 10 to the negative first. The reason why it's negative is because I'm moving the decimal to the opposite direction. When performing operations such as adding, subtracting, multiplying, and dividing, you can memorize rules from doing this with numbers written in scientific notation, or you can convert them to standard form, perform the operation, then convert the answer back into scientific notation. The example that I gave was, for example, the United States has about 320 million people. The world's population is about 7.5 billion. How many times does the population of the United States fit inside the world? So what I did is I wrote both of those numbers in standard form and in scientific notation by following the procedure I just outlined. So 320 million in scientific notation is written as 3.2 times 10 to the 8th, and 7.5 billion is written as 7.5 times 10 to the 9th. So the actual numbers in standard form are written here, and if you were to calculate that, you would see that it's about 23.4 times. I did that to let you see how cumbersome this is with long division as compared to writing the numbers more simply with fewer digits. Another reason scientific notation is used is to show the expanse or smallness of an object. A human red blood cell, for example, is about 100 micrometers in diameter, give or take. The size of this is 1 times 10 to the negative 6 power. Written in standard form, it's a decimal point, 5 zeros, and then a 1. Here's another example of why scientific notation is important and why expanding a part of a number line can show important differences that may not seem obvious. So in this example, what you've got is how fast electricity moves through different mediums. The medium that electricity passes through determines how quickly power is delivered or not delivered to a place. So olive oil, water, ice, and copper wire, not sure why they chose these examples, but they all fall in this little range in this top part of the number line. And here it doesn't look like the differences are that much, which they aren't. But when you're working with digits this big, even when points are clustered along a number line, there's still a fair amount of difference that's being worked. So that's why this part of the number line here is expanded. And we included additional place values to show. So here's a 2, here's a 3, so that would make this 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9, and then it goes to 3. This table here shows these numbers written in both scientific notation and standard form. Even though a diamond, which is right here, isn't very far from, let's say, olive oil, which would be the next point, the speed between those two is 76 million meters per second. That's really, really fast. So even though they don't look that far apart, it's still important to see why it's important to expand a part of a number line to show you that even though they're clustered together, when you look at the actual numbers, they're not that close together. The difference between water and ice, for example, 225 million versus 230 million meters per second, that's still 5 million meters per second. That's fairly significant, 5 million meters per second. That's really fast. And then copper wire is 50 million meters per second faster than ice. So just looking at that, you again see the reason why you should have to expand part of a number line in order to be able to recognize the differences. All right, let's look at exponents here, the rules. They're not complicated once you get the hang of it. I found that there are 4 main ones to remember. When exponents are multiplied without parentheses, you add them. When exponents are multiplied with parentheses, you multiply them. When exponents are divided, you subtract them. When exponents are written as negatives, you write the inverse of them. Think of reciprocals from dividing fractions, which is one of the reasons why I kept saying this over and over and over again this year. All of these rules apply when the variables match. You wouldn't subtract a y from a z or an x from a q, for example. They have to match in order to apply these rules. And most importantly, always, always follow order of operations. When following order of operations, you'll be good to go. If you don't, then you will probably get the answer incorrect. You've got to remember to follow what's in parentheses first, then do the exponents after that. Okay, everybody, I'm going to show you step by step how to do all these exponent questions so that you will do well on your minor, but more importantly, so that you do well when you get into Math 1 next month. So let's look at this first question. This is 6x cubed times 4x to the 5th power. So when we're multiplying here, we actually will multiply the coefficients, which would become 24. But then, like I was saying in our exponent rules, we're going to add the exponents powers anyway, because the variables are the same. My variable is x, and then 3 plus 5 is 8. At this point, this can't be simplified anymore, so my answer is 24x to the 8th power. Let's look at the second question example here. In this one, I have y to the 7th, z to the 6th power over y to the 5th, z to the 2nd. Now, this is just like expressions. I don't know what y and z are, and that doesn't matter, because my goal here is to simplify, not solve. Because this is a division question, the rules stipulate that we would actually subtract them. At least we subtract the ones where the variables are the same. 7 minus 5 is 2. So I end up with y squared, and I write it up top because the 7 was on the top, not the bottom. And then 6 minus 2 is 4. So my simplified answer is y squared z to the 4th. I can't combine these because the variables are different. Let's look at my third example here. In this example, I've got x to the 4th, y cubed over x to the 6th, y to the 4th. This is going to work similarly to the question that's above it. The difference with this one, however, is that my larger numbers are all in the denominator, so what's left will be written there. 4 take away 6 is 2, leaving me with x squared. And 3 minus 4 is 1, so I'm just going to write y. That's left in my denominator. If there is no number to write in the numerator, I've just put 1 as my answer for that. Now let's get into something a little bit more challenging with negative exponents. Here I've got y to the negative 6th power, w to the negative 6th power, and then y to the 6th power. Anytime that an exponent is written as a negative, it's not simplified. The simplified version is to write its reciprocal. The reciprocal of y to the negative 6th power is to write it in the denominator as a positive. So I'm going to write and move that here, y to the 6th, or w to the 6th power. Y to the 6th doesn't change. So my simplified answer is y to the 6th power over w to the 6th power. In my next example, I've got 4cd to the 4th squared times 6c squared d squared cubed. I'm going to follow order of operations. There's nothing to combine inside each terms of the parentheses, so now I'm going to apply this exponent of 2 to everything on the inside. 4 cubed is 16. C to the second is c squared. D to the fourth squared becomes d to the eighth times 6 cubed is 216. C squared to the third power would become c to the sixth. D squared to the third power becomes d to the sixth. But at this point, I'm still not finished. Now I need to multiply 16 times 216 and then add the exponents for c and d. So I want to do that first really fast. That's going to give me c to the 8th and d to the 14th power. And then I just need to multiply 216 times 16, which I'm going to do really fast while you are looking at this. That gives me 3,456 c to the 8th, d to the 14th. And then I'm finished. My next example is 7x to the negative 4th, y to the negative 3rd, over 4x to the negative 3rd, y to the negative 5th. Now before I do anything, I need to write the reciprocals of my negative exponents here. 7 and 4 aren't going to change. Those coefficients stay exactly where they were. So I'm going to write 7 over 4 and be done. Then I'm going to reverse the positions of these and move them up top. And then these ones here, I'm going to move down to the bottom. So that becomes x cubed, y to the 5th, and then x to the 4th, y to the 3rd. Now I can simplify this more by subtracting my x's. That's going to be gone, leaving me just with x. And then 5 minus 3 is 2, but that would go up top. So my simplified answer is 7y squared over 4x. Now I'm going to give you a super challenge question. I want to see if you can do this. I want you to hit pause after I've written it and then test it and then work it out on your own. So here's the question. Parentheses, negative 7a squared b cubed c to the 0 power over 3a cubed b to the 4th c to the 3rd applied to the negative 4th power. First thing I need to do is change this into a positive. To do that, I'm going to reverse everything on here. My denominators go up top, my numerators go down to the bottom. So I'm going to rewrite it, 3a cubed b to the 4th c to the 3rd over negative 7a squared b cubed c0 now over equal to the 4th power. Now I'm going to attempt to simplify this. 3 and 7 aren't going to change. I'm just going to rewrite those here. A cubed minus a squared just leaves me with a. B to the 4th minus b to the 3rd just leaves me with b. C0 is just equal to 1, so I'm just going to write c cubed over again. And now I can apply the exponent of 4 to everything. So 3 to the 4th power is equal to 81. A to the 4th, b to the 4th, c to the 12th, and then negative 7 to the 4th power equals positive 2,400.